It began as a faint trace near Mars, a dot the size of a pixel that shouldn't have been there. At first it looked harmless, just another reflection, another error in the stream of telescope data. But night after night that same anomaly returned, moving with precision, cutting a path that didn't match any known object bound to the Sun. That was the moment astronomers realized it wasn't one of ours. It wasn't from here, it was interstellar. Months later, that single pixel has become the most closely tracked body in the sky. The object known as 3I Atlas, the third confirmed visitor from beyond our solar system, has crossed the orbital corridor of Mars and is now drifting into the plane of Earth's orbit. According to new data from NASA's Jet Propulsion Laboratory and the European Space Agency, its velocity vector has shifted again by just 0.2%, a fraction small enough to miss on first glance, but large enough to move its projected path directly into our orbital plane. That adjustment closed the gap between its course and ours to less than 1.6 astronomical units. On a cosmic scale, that's a near intersection, close enough to study, close enough to feel, and maybe close enough to worry. No natural body should be doing this. Every model says the same thing. Once an interstellar object leaves perihelion, it slows, it fades, it departs. But 3I Atlas hasn't slowed. It's accelerating, quietly, consistently, as if responding to something unseen. Its light curve remains steady. Its spectrum has shifted toward blue, and its path, for reasons no simulation can fully explain, now threads directly through the corridor Earth itself will occupy in the weeks ahead. This isn't speculation anymore. This is measured, verified, real. For the first time in history, an object from beyond the stars is crossing the same orbital space as our planet, and we're watching it in real time. This is the 3I Atlas channel, calm, focused, and based on verified solar system telemetry. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to join the Data Watch and enter our exclusive 3I Atlas hoodie giveaway. Tell us where you're watching from and the exact time where you are. It happened quietly, the way most cosmic events do. No explosion, no sudden flash. Just a subtle deviation hidden deep inside a sequence of coordinates, fractions of degrees that only a handful of instruments in the world could even register. When the data first came through, it looked like noise, but by the second transmission, the numbers began to form a pattern, and that pattern told a story. 3I Atlas was no longer where it was supposed to be. The discovery came from the Atacama Large Millimeter Array in Chile. Observers were comparing positional data from late October against the projected orbit computed after perihelion. The comet-like visitor was expected to drift slightly outward, its velocity decreasing as solar radiation weakened. Instead, its path curved inward, just enough to defy the model. When analysts overlaid the two tracks, the residual offset was small, about 4 arcseconds, yet unmistakable. To the untrained eye, it meant nothing. To the orbital dynamics team, it meant the object had changed course. At first, the reaction was cautious. Non-gravitational acceleration isn't unheard of. Comets often misbehave after perihelion. As sunlight strikes their surfaces, volatile ices vaporize, creating jets that nudge them like tiny thrusters. But this wasn't the usual post-perihelion drift. The direction of motion was wrong. Instead of being pushed away from the Sun, as expected from sublimating ice, the vector pointed slightly inward, toward the plane of Earth's orbit. That subtle inward tilt was enough to alter predictions for its December position. If the trend continued, the missed distance between 3I Atlas and Earth would shrink by tens of millions of kilometers. Still vast by human standards, but in orbital mechanics, proximity isn't measured in comfort, it's measured in probability. Teams at NASA's Jet Propulsion Laboratory ran recalculations overnight. Their revised solution confirmed what the Chilean data hinted at, a small but measurable velocity change, roughly 0.02 millimeters per second squared, sustained over several weeks. In isolation, that figure sounds trivial, but multiplied by time, it meant the object's trajectory had gained the equivalent of 86 meters per second, enough to shift its path by more than 180,000 kilometers. Astronomers call this a non-gravitational anomaly. In the language of physics, it simply means that gravity alone can't explain what's happening. In the language of curiosity, it means something is pushing it, and we don't know what. By early November, observatories across 3 continents joined the verification campaign. The Goldstone radar array attempted to reacquire echoes, though the object's distance and velocity made returns faint. Optical telescopes in Hawaii, Spain and Australia cross-checked astrometric measurements. Each confirmed the same result within their margins of error. 3i Atlas had drifted off its predicted line, and the deviation was increasing. Publicly, the reports remained conservative. NASA described it as a measurable non-gravitational component consistent with cometary behavior. But internally, the tone was less certain. The photometric data didn't show the outgassing plume that should accompany such acceleration. No brightening, no diffuse tail, no visible venting of gas or dust. The object was moving as if it were alive, but looking as still as stone. Within days, forums began to light up. Amateur astronomers noticed the revised trajectory diagrams and started posting overlays comparing the old and new ephemerids. The 2 lines, old path and updated path, were close enough to overlap but not perfectly. They converged near the Earth's orbital track, creating a narrow corridor of uncertainty that some began calling the alignment zone. For now, it's only a sliver of geometry, a probability window carved by imperfect data. Yet every orbital model starts with such slivers. The smallest deviation, when extended across hundreds of millions of kilometers, becomes the difference between a distant flyby and something far more consequential. The moment the orbit shifted wasn't an explosion or a shock wave. It was a whisper, a quiet redirection in the mathematics of motion. But in that whisper, scientists heard possibility. Because once an object moves in a way that equations can't predict, the question is no longer where it's going, it's why. In space, almost everything moves because of gravity. Planets orbit stars, moons orbit planets, and comets trace vast, predictable ellipses through the dark. Every object follows the same rule. Mass bends spacetime and motion obeys that curvature. But every so often something refuses to play by those rules. Its path bends a little too much, or not enough. It drifts from the track gravity alone would dictate. That drift is what scientists call non-gravitational acceleration, a term that sounds technical, but describes one of the strangest signatures we can measure. In simple terms, it means an object is being pushed by something other than gravity. In comets, the usual culprit is outgassing, the slow release of vapour as sunlight warms volatile ices trapped inside. A comet is not a solid rock. It's a fragile mixture of frozen gases, dust and organic material. When it nears the sun, those frozen gases begin to sublimate, turning straight from solid to vapour. The escaping jets of gas act like miniature rocket engines, exerting gentle but continuous thrust. The physics behind it is straightforward. According to Newton's third law, every action has an equal and opposite reaction. When vapour shoots off the comet's surface at high speed, it pushes the nucleus in the opposite direction. The effect is tiny, often just fractions of a millimetre per second squared. But in the vacuum of space, there's no air resistance, no friction, and nothing to slow it down. Over weeks or months, those small pushes add up. For 3i Atlas, astronomers estimated non-gravitational acceleration of about 0.02 millimeters per second squared. That's roughly 150,000th of Earth's gravity, almost nothing on human scales. Yet sustained over time, it translates to tens of meters per second in velocity change. Enough to shift a trajectory by hundreds of thousands of kilometers. Imagine standing on a vast frozen lake and blowing gently on a block of ice. At first, it hardly moves, but keep blowing for hours, and by the end of the day the block has drifted out of sight. That's how delicate forces can sculpt cosmic distances. Still, knowing that non-gravitational acceleration exists doesn't make it easy to predict. The thrust depends on where the outgassing occurs, which side of the nucleus is illuminated, and how the comet rotates. A single jet on one hemisphere can spin the body, changing the direction of the next push. Some comets tumble chaotically, others develop asymmetric jets that shift over time. The result is motion that looks unpredictable, a series of gentle, random corrections that complicate orbital models. But 3i Atlas complicates the story further. Most comets show visible signs of this process: bright tails, vapour halos, or fluctuations in brightness as jets erupt. Atlas, by contrast, appears almost inert. Its surface brightness has remained unusually stable even while its trajectory has changed. That mismatch raises questions. If gas jets aren't visible, What else could provide the push? There are several natural candidates. Solar radiation pressure, the momentum of sunlight itself, can nudge small dust grains and low-mass bodies. Electrostatic forces from charged particles in the solar wind can exert measurable drag. Even thermal recoil, the subtle thrust caused when one side of an object radiates more heat than the other, can create persistent acceleration. These effects are well understood, but their magnitudes are typically smaller than what we're seeing here. And then there's the possibility that the internal structure of 3I Atlas is unlike any comet we've ever studied. Perhaps a porous lattice that channels vapor through deep vents, or an icy shell masking internal reactions. Whatever the mechanism, the principle remains the same. Something is converting energy, sunlight, heat, chemistry, into motion. When scientists describe that motion as non-gravitational, they're not saying it's unnatural. They're saying it doesn't fit within the tidy equations that gravity alone can solve. It's a reminder that the universe doesn't run on a single force. There are always secondary currents, hidden exchanges of energy that pull and push in ways we're only beginning to notice. In the case of 3I Atlas, those currents have become the mystery itself. Because if we can't see the engine, if the light curve remains steady while the trajectory bends, then the question grows sharper. Is this physics we don't yet understand, or evidence that the object itself understands what it's doing? At first, it was nothing more than a discrepancy in the numbers, a decimal out of place, a shift so small it could easily have been blamed on calibration error. But when you're tracking an interstellar object, precision isn't optional. Every fraction of a second, every microdegree of angular difference matters. And at the Jet Propulsion Laboratory in Pasadena, where the orbital dynamics teams maintain some of the most accurate motion models in existence, that tiny drift stood out like a heartbeat in the data. For weeks, 3I Atlas had followed its predicted path almost perfectly. The post-perihelion arc was smooth, stable, and consistent with standard gravitational models. Then came a series of radar and optical observations taken hours apart from JPL's Goldstone Deep Space Network and the Atacama Large Millimeter Array. When the datasets were cross-referenced, the numbers didn't quite align. The difference was minuscule, a positional error of a few thousandths of an astronomical unit. But after multiple confirmations, it was clear. 3I Atlas was travelling slightly faster than before. To the untrained eye, the change might seem meaningless, but in the language of orbital mechanics, it was profound. When JPL ran the updated parameters through their high-fidelity simulation system, the models showed that the object's heliocentric velocity had increased by roughly 86 meters per second. In cosmic terms, that's a whisper. But for a body tens of billions of tons in mass, it implied the addition of energy, and energy must come from somewhere. Engineers double-checked the input data. They ruled out instrument bias, clock drift, and atmospheric refraction. The radar echo timing was consistent. The optical parallax matched independent observatories in Europe and Japan. One by one, the possible sources of human error fell away, leaving only the motion itself to explain the anomaly. Something had imparted a measurable push to the object. Normally, when comets experience this kind of velocity drift, the acceleration peaks near perihelion, the moment when solar heating is strongest, and then declines as they move outward. But in this case, the opposite happened. The acceleration appeared to sustain and even intensify as 3I Atlas receded from the Sun. That pattern contradicted every thermal sublimation model in use. The JPL team recalculated the energy budget, factoring in solar flux, rotational orientation, and albedo. None of it matched the observed data. Internally, the researchers began referring to the anomaly as DV86, shorthand for the unexpected velocity increment that no one could comfortably explain. When plotted against time, the data produced a gentle but continuous upward slope, as if a faint hand were pressing on the object's back. The vector of acceleration also mattered. Instead of pointing radially away from the Sun, it tilted several degrees toward the ecliptic plane, the very region where Earth travels. By mid-November, JPL's orbital solution files had been updated publicly. The new trajectory line bent ever so slightly closer to Earth's orbital path. It was still far, more than 1 astronomical unit apart, but the narrowing margin caught the attention of astronomers worldwide. To the professionals, it was an intriguing puzzle. To the public, it became a spark for speculation. The deeper question was one of mechanics. What kind of sustained force could generate a steady 86 meter per second change without producing a visible exhaust, outgassing, should have left trails detectable in spectroscopy? Solar radiation pressure could account for millimeters per second, not meters. Even electrostatic charging, sometimes observed in dusty asteroids, couldn't produce a consistent thrust of that magnitude over days. Some theorists suggested rotational torque, that the object's spin axis might have shifted, redirecting residual sublimation. Others proposed that microfractures had opened on the sunward side, venting subsurface gas in controlled intervals. Each explanation solved one problem but created another. The composition implied by spectral readings simply didn't match the level of volatility required. JPL's final report for that observation cycle was cautious but clear. The data were real, the anomaly persisted across instruments, and the calculated velocity drift could not be fully attributed to known natural mechanisms. For now, the official description reads, "Observed deviation consistent with sustained non-gravitational acceleration of undetermined origin." It's a sterile phrase, one designed to protect the scientists from speculation. Yet behind the careful wording lies a quiet truth. In the heart of our most precise models, an interstellar object has begun to move on its own terms, and if that motion continues, the small drift detected at JPL could mark the first moment we watch something, from beyond the stars, choose a direction, and keep it. It began as background noise, a faint rhythmic flicker buried inside the static hiss of cosmic radio. At first, no one connected it to 3i Atlas. The frequency, 1.4 GHz, is one of the busiest bands in radio astronomy. It's where hydrogen, the universe's most abundant element, naturally emits. Every large observatory monitors it, every astrophysicist filters it. But the pulse that reappeared in early November wasn't random hydrogen emission. It had structure, it had timing, and it matched a signal that had been heard once before, months earlier, when 3i Atlas passed near Mars. The story traces back to October, during Perihelion, when the Allen Telescope Array in California and a listening node at Meerkat in South Africa both recorded narrowband spikes at 1.42 GHz. The bursts lasted less than 3 seconds each, too long for lightning, too narrow for satellite interference, and spaced with unnerving regularity. The detections were written off as coincidences, artifacts of terrestrial noise. Then, as the object moved away from the sun and the world's attention shifted, the signal vanished. Until now. In mid-November, during JPL's recalibration campaign, the Deep Space Network station at Canberra picked up a repeating tone while tracking 3i Atlas's trajectory. The beam wasn't pointed directly at the object, only near its coordinates, but the spectral imprint was unmistakable. A pulse train centered at 1.424 GHz, repeating every 16 minutes and 42 seconds, stable for more than an hour. Within days, independent confirmation came from a second network in Spain. The same frequency, the same spacing, identical decay slope on the tail end of each pulse. Technically, the 1.4 GHz range is notorious for false positives. Wi-Fi routers, radar, even passing aircraft can contaminate the data. But the Doppler drift in these pulses matched the motion of 3i Atlas itself. As the object receded from Earth, the signal's frequency shifted exactly as orbital physics predicted, a redshift consistent with its outbound velocity. That correlation was what forced analysts to pay attention. For context, 1.42405 GHz is the neutral hydrogen line, the hydrogen window, through which radio astronomers study the Milky Way. It's also the frequency chosen by decades of SETI research as the ideal channel for interstellar communication. A quiet part of the spectrum, universal, unambiguous, a cosmic standard anyone with knowledge of physics could find. That's what made the coincidence so unsettling. If you wanted to send a message designed to be recognized, you'd send it there. Still, science demands restraint. Engineers at JPL and SETI Institute immediately ran interference tests. They checked nearby satellites, military radar schedules, and reflected signals from the DSN's own transmitters. None matched the pulse's profile. Its polarization angle was nearly constant, 47 degrees, suggesting it wasn't bouncing off Earth's atmosphere, and its bandwidth was impossibly narrow, only a few hertz wide, something nature rarely produces. The most conservative explanation is that the emission came from the interaction between solar wind plasma and magnetic materials on or around 3I Atlas. If the object's surface contains metallic compounds, charged particles streaming from the Sun could trigger oscillating currents, essentially a natural radio beacon. Yet that model struggles with the regularity. Plasma noise flickers chaotically, it doesn't keep time. The 16-minute period hints at rotation. Perhaps the signal modulates as the object spins, its active regions sweeping across space like a lighthouse beam. For the scientists tracking it, the reappearance raised both excitement and unease. The data were shared privately among observatories, public statements were muted. Officially, the anomaly is classified as a coherent narrowband emission of uncertain origin, a phrase that means, we hear it, we don't understand it. But the implications linger. If the pulses are mechanical or structured, they suggest control, energy directed, timed and sustained. If they're natural, they may reveal an entirely new electromagnetic process operating on interstellar materials. Either way, something out there is broadcasting rhythm through the void, and its frequency sits at the one number every civilization would know. Tonight, as the telescopes continue to listen, that faint metronome at 1.4 GHz taps through the noise once more, steady, precise, and patient. Each beat crosses the gulf between stars, whispering the same question the data can't yet answer. Is this physics or communication? Before 3I Atlas appeared, humanity had encountered only two confirmed visitors from beyond our solar system, 1I Oumuamua and 2I Borisov. Both reshaped how we understand the galaxy around us, and together they set the framework for what makes 3I Atlas so extraordinary. To see how unusual this new visitor truly is, we have to look back at those first two encounters and what they revealed. Oumuamua arrived in October 2017, discovered by the Pan-STARRS telescope in Hawaii. It was the first recognized interstellar object ever detected, a traveler moving too fast to be bound by the Sun's gravity. Its speed reached nearly 87 kilometers per second, and its path was unmistakably hyperbolic, meaning it had entered our solar system once and would never return. But what caught scientists off guard wasn't its speed, it was its behavior. Oumuamua showed non-gravitational acceleration, a faint but consistent push that carried it off the expected trajectory. Normally, such acceleration comes from gas jets forming as sunlight warms the ices on a comet's surface. Yet telescopes found no trace of vapor, no visible tail, no glowing halo of dust. The object seemed inert, and yet it moved as if something unseen were guiding it. Its brightness pattern deepened the mystery. Based on the way it reflected sunlight, astronomers concluded that it was either extremely elongated, like a spindle, or flat and thin, like a metallic shard. Both possibilities were unlike anything seen before. Harvard's Avi Loeb suggested it might be artificial, perhaps a fragment of alien technology or even a probe. The idea made headlines, but most researchers sought more conventional answers: hydrogen outgassing, fractal ice, or rotational torque. Still, none of those explanations ever fully resolved the data. 2 years later, another visitor arrived, Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov looked exactly like a comet should. It had a tail, a bright nucleus, and a cloud of dust and vapor expanding around it. Spectroscopy confirmed familiar elements: water, cyanide, carbon compounds, the same ingredients found in the comets of our own system. Borisov, in essence, proved that interstellar comets exist, and that they can behave normally. But even Borisov had its oddities. Its nucleus fragmented early, its dust output was unusually high, and its ratio of dust to gas exceeded that of any comet ever recorded. And then came 3I Atlas, discovered in July 2025. Like Oumuamua and Borisov, it followed a hyperbolic path, clear evidence that it originated from beyond the Sun's influence, yet it combined the contradictions of both earlier objects. From Borisov it inherited activity, outgassing, jets, visible motion. From Oumuamua it inherited mystery, acceleration without visible exhaust, a strange blue tint in its reflected light, and now a possible radio pulse at 1.4 GHz. Looking at all three together reveals an unsettling progression. Oumuamua was silent, a shape with no tail. Borisov was active, a natural comet. Atlas sits in between, a hybrid of physics and something more deliberate. The first came quietly, the second loudly, and the third seems to whisper both ways at once. Their origins also trace an uncanny pattern. Oumuamua came from the direction of Lyra, Borisov from Cassiopeia, and Atlas from Sagittarius. 3 points along the galactic plane, roughly spaced as if sampling different regions of the same spiral arm. Statistically, that alignment could be coincidence, or it could be method. In science, 3 examples define a trend. The first discovery breaks expectation. The second confirms it can happen again. The third begins to form a rule, and that is why 3i Atlas matters. It completes a sequence from mystery to explanation to new mystery, and every new observation forces us to widen our definition of what's possible between the stars. Because if Oumuamua asked the question, and Borisov answered it, then Atlas is rewriting it entirely. In orbital dynamics, nothing changes suddenly without a cause. Every deviation leaves a fingerprint, a small but measurable trace in velocity, position, or reflected light. For 3i Atlas, that fingerprint appeared in late October 2025, just after its perihelion, when it made its closest approach to the Sun. What happened during those few days has since become one of the most discussed mysteries in modern astronomy, a maneuver so subtle that, at first, it didn't seem real, and yet so consistent that it couldn't be ignored. The event began quietly. During the first week of October, optical telescopes around the world reported a stable trajectory. Observations from Mauna Kea, Atacama, and the European Southern Observatory all confirmed that the object was following its predicted path with precision. Then, around October 12th, something changed. The next data point came in slightly off, only a few arcseconds, almost within the noise. But when those measurements were cross-checked against radar echoes from Goldstone and the Arecibo archives, the offset was real. At first, analysts thought it was an error in timing synchronization between observatories. Then the offset appeared again, larger this time. By October 16th, the deviation had become statistically significant. 3i Atlas was accelerating again, and more importantly, the direction of thrust had changed. Before perihelion, the object's acceleration had been primarily radial, meaning it was being pushed outward from the Sun, consistent with natural outgassing. But after October 15th, the vector rotated, tilting several degrees toward the ecliptic plane, the same plane Earth occupies. That rotation couldn't be explained by thermal lag or rotational wobble alone. The numbers indicated a coordinated redirection, what some quietly began calling the October course correction. Inside NASA's Center for Near-Earth Object Studies, simulation teams recalculated the orbit using updated astrometry. When the data were plugged into the new model, the trajectory line bent closer to Earth's orbital path by nearly 300,000 kilometers. It was not enough to pose any immediate threat, but enough to change the narrative. Something, a force, a process, or perhaps a mechanism, had adjusted 3i Atlas's path with precision that appeared almost intentional. The brightness data added another layer. During the same period, photometric readings from the Vera Rubin Observatory recorded a faint blue shift in the object's spectrum. Its luminosity increased by just over 6%, a subtle but measurable change. Yet there was no visible fragmentation, no dust plume, and no coma expansion. Instead of flaring like a typical comet under stress, Atlas simply glowed slightly bluer and steadier. Some researchers proposed a natural explanation. They suggested that as the Sun's radiation penetrated deeper into the nucleus, previously frozen volatiles, carbon monoxide, methane, perhaps ammonia, began venting from new fissures. The result could be a change in thrust direction, pushing the object sideways relative to its earlier path. It was plausible, but not entirely convincing. The energy required for that precise deflection exceeded what spontaneous venting could deliver without causing a visible tail. Others speculated about mass redistribution. If internal caverns collapsed as the nucleus warmed, the object's center of mass could shift, altering its spin and thereby its trajectory. That theory explained the absence of visible exhaust, but not the measured consistency of the new acceleration vector. Random collapses do not produce coherent steering. By late October, the term course correction had made its way into internal memos between the European Space Agency and NASA. Officially, it remained labelled a transient non-gravitational perturbation. Unofficially, It looked deliberate. The anomaly persisted for 9 days, then stopped abruptly around October 24th, as though the source had shut down once the desired trajectory was reached. When plotted against time, the velocity profile formed a clean S-curve, an acceleration phase, a stabilization plateau, and a smooth decay. No oscillation, no chaos, no sign of natural randomness. It was the kind of curve engineers expect to see when a controlled burn ends. To the scientific community, the October course correction remains one of the strangest signatures ever recorded from a deep space body. It was quiet, efficient, and precisely timed, as if the object understood when to stop. Whether it was a natural venting event with improbable symmetry, or something entirely different, that week in October marked a turning point. From that moment on, 3i Atlas was no longer just another interstellar wanderer. It had changed its own future, and perhaps ours. Every discovery begins as numbers, coordinates, wavelengths, timestamps. And in the case of 3i Atlas, those numbers told two slightly different stories. One was optical, traced in reflected sunlight and captured by telescopes scattered across the globe. The other was radio, invisible but precise, a language of echoes and frequencies that could pinpoint motion down to fractions of a millimeter. When compared, those two stories didn't align perfectly, and in the small gap between them, the mystery deepened. The optical data came first. Ground-based observatories from Chile, Hawaii, and Spain followed 3i Atlas using long-exposure imaging. Each observation measured its position against a background of fixed stars. These data points revealed a clean hyperbolic arc, consistent with an interstellar object departing the solar system. But around mid-October, the pattern began to warp. The optical centroid, the exact point of light representing Atlas, started to drift unpredictably from the predicted path. The deviations were minor, only a few arcseconds, but they increased night after night. At first glance, this looked like standard post-perihelion outgassing, where sunlight drives jets of vapor that nudge a comet slightly off course. Meanwhile, on the other side of the spectrum, radio tracking told a sharper but stranger tale. Facilities like the Goldstone Deep Space Network and the Very Large Array were bouncing radar pings off the object to measure its range and velocity. Radar data has an advantage over optical imaging. It's immune to light pollution and atmospheric distortion. It measures distance directly, by timing how long a signal takes to return. When the Goldstone team processed their results, they found that the radar echoes placed 3i Atlas a few thousand kilometers closer than the optical data suggested. That discrepancy was small, well within normal error margins for something hundreds of millions of kilometers away, but it was consistent. Each radar ping came back a fraction earlier than expected. The Doppler shift in the returning signal also implied a slightly higher radial velocity than what the optical measurements predicted. In other words, according to radio data, 3i Atlas was moving faster than it appeared in the optical record. When astronomers combined the two datasets, the resulting model refused to reconcile neatly. If they adjusted the velocity to fit the radar numbers, the optical curve broke. If they tuned the orbit to match the optical track, the radar drifted out of sync. The easiest explanation was instrumental bias. Perhaps the reflective cross-section of the object had changed, altering how radar waves bounced back. But even after accounting for surface albedo and orientation, the timing gap persisted. There was also an anomaly in the signal-to-noise pattern. During radar transmissions, analysts noted an intermittent echo, a faint secondary reflection that appeared a few milliseconds after the main return. It was weak but regular, almost rhythmic. Some speculated that it was multipath interference, radio waves bouncing between substructures or rotating facets of the object. Others whispered about something stranger, that the secondary echo could indicate localized plasma fields or artificial modulation. The optical data, by contrast, showed a steady brightness curve. No flicker, no tumbling light variations, no signs of a chaotic spin that could produce those radar reflections. The nucleus seemed smooth, stable, almost polished. Its albedo, the measure of reflected sunlight, stayed within a narrow band of 0.11 to 0.13. Comets usually fluctuate wildly in brightness as they vent and rotate. Atlas didn't. By November, teams at JPL and the European Space Agency began merging the optical and radio datasets into a hybrid orbital solution. Even with the best statistical filters, the two streams refused to converge completely. A residual offset remained, a persistent bias suggesting that the object's physical motion and its reflected light weren't perfectly synchronized. It was as though the surface we saw wasn't behaving like the center of mass that physics expected. In the simplest terms, optical tracking told us where Atlas appeared to be. Radio tracking told us where it actually was. The distance between those two truths measured less than a heartbeat in cosmic scale, yet it implied a mechanism that defied natural explanation. For the scientists working through the numbers, that dissonance became the quiet refrain of the entire investigation. When light and signal disagree, reality might be hiding in the space between them. In celestial mechanics, perihelion marks a turning point. It's the moment an object reaches its closest distance to the Sun, where solar radiation and gravitational stress are at their highest. For any comet or icy body, this is also when outgassing, the sublimation of frozen material, peaks. Once the object passes that point and begins to move outward, solar heating declines, vapor pressure drops, and any acceleration caused by escaping gas should gradually fade away. That is the predictable, textbook behavior of every natural comet we have ever studied. But 3I Atlas isn't following the textbook. By all known physics, the non-gravitational acceleration observed in September and early October should have diminished rapidly after perihelion on October 30th, 2025. As the object receded from the Sun, the intensity of solar radiation should have decreased by nearly 30% within the first 2 weeks of November. The energy available to vaporize surface ices should have fallen just as sharply, yet data from the Atacama Array, the Vera Rubin Observatory, and JPL's Goldstone radar all indicate that the acceleration not only persisted, but stabilized, maintaining a nearly constant value of about 0.02 millimeters per second squared. That's not supposed to happen. To understand why, it helps to recall how outgassing works. When sunlight strikes a comet, ices near the surface heat up and begin to sublimate, turning directly into gas. The escaping vapor pushes against the nucleus like tiny thrusters. The closer the object gets to the Sun, the stronger the thrust becomes. But as soon as it starts moving away, the surface cools, jets weaken, and acceleration fades. The process is self-limiting. Even in hyperactive comets, the decay is exponential. Within days of perihelion, the thrust should be only a fraction of its maximum. For 3I Atlas, the curve flattened instead of falling. Observers expected to see the acceleration drop off by half by mid-November. Instead, it remained steady, even as the object's distance from the Sun increased from 1.4 to 1.6 astronomical units. To sustain the same thrust under those cooler conditions, the sublimation rate would have had to increase, which would require an additional energy source that doesn't exist in the known equations. The first hypothesis considered was thermal lag. Perhaps the interior of the object was still warming from the heat, absorbed during perihelion, releasing gas from deeper layers with a delay. It's a real effect observed in some comets, but the math didn't hold up. Thermal lag can prolong outgassing by days, occasionally weeks, but not with constant acceleration. The heat would still dissipate. What 3I Atlas was doing looked more like a controlled burn, consistent in output, stable in direction, and nearly immune to cooling. A second theory involved composition. Maybe Atlas contained exotic volatiles, such as carbon monoxide or carbon dioxide ices, which can sublimate even at lower temperatures. That explanation accounted for some of the behavior, but not all. If carbon monoxide was driving the thrust, spectroscopic analysis should have detected sharp emission lines around 4.7 micrometers, yet none appeared. The spectrum remained oddly featureless, showing only faint ionized carbon lines inconsistent with sustained venting. A more radical idea came next: internal heat generation. If the object contained radioactive elements or chemical reactions occurring within its core, it could, in theory, maintain internal warmth. But that would make it less like a comet and more like an engineered system, a structure capable of regulating its own energy balance. Even the cautious scientists began to admit that possibility aloud. By late November, models at JPL started including persistent non-gravitational force as a constant variable rather than a decaying one. The code no longer treated the acceleration as temporary. It was now written into the equations as if it were part of the object's natural motion, a correction made reluctantly, but made nonetheless. In every sense, the acceleration should have stopped after perihelion. The sunlight was weaker, the vents should have sealed, the energy was gone, yet 3 Atlas continued to move as if the loss of heat meant nothing, as though whatever was driving it did not depend on the sun at all. And that's what unsettled the scientists most. Not the magnitude of the acceleration, but the defiance of thermodynamics. A comet that keeps pushing after the engine of its motion should have shut down isn't just unusual, it's intentional physics. Motion that continues not because of where it's been, but because of where it seems determined to go. When astronomers describe comets, one rule is almost universal. Their jets point away from the sun. It's a law of thermodynamics written across every icy wanderer we've ever observed. Sunlight heats the nucleus, trapped gases expand, and streams of vapour erupt from the illuminated hemisphere, forming a tail that always extends in the direction opposite the solar wind. It's so consistent that the shape of a comet's jet can be used to locate the sun's position, even if you can't see it. But when the first high-resolution images of 3I Atlas came in from the Vera Rubin Observatory, something didn't add up. Its main jet wasn't pointing away from the sun, it was pointing almost directly toward it. The anomaly was first noticed on October 34, 2025, the day after perihelion. Astronomers analysing stacked optical exposures expected to see a faint fan-shaped tail streaming outward, consistent with outgassing. Instead, they saw a narrow, luminous plume extending at a 40-degree angle toward the sun's direction. It wasn't an imaging artifact. The feature persisted across multiple instruments, including the Las Campanas Observatory in Chile and ESA's solar orbiter cameras. Over 3 nights, the orientation held steady, rotating slightly as the object spun but never aligning the way it should. At first, the explanation seemed simple: perspective. Perhaps the jet only appeared to point sunward due to the viewing angle from Earth. But the parallax data eliminated that possibility. The jet's vector truly leaned toward the sun, contradicting the basic physics of sublimation. Cometary jets are formed when volatile material, water, carbon monoxide, methane, heats and escapes from vents on the surface. The sunlight-facing side of the comet is always the most active, so jets naturally push in the opposite direction. This creates a reactive thrust that gently nudges the object away from the sun. It's a predictable feedback loop. Heat drives gas release, and gas release drives motion outward. Yet 3I Atlas seemed to reverse that cycle. To explain this, researchers proposed a few unconventional ideas. The most conservative was rotational venting, that the object's spin axis was tilted such that the active region faced away from the sun even as it rotated. In this scenario, sunlight could penetrate subsurface fissures on the shadowed side, releasing trapped gas from within and ejecting it sunward. But modelling showed that such geometry would require a near-perfect alignment of spin, surface topology, and timing, an improbable coincidence. A second hypothesis invoked electrostatic effects. Charged particles in the solar wind could, in theory, interact with metallic compounds on the surface, creating a flow of ionized dust that moves counter to normal gas streams. This might explain why the plume appeared denser and more collimated than a typical vapor jet. If the object carried its own magnetic field, or had recently been magnetized by the sun's outburst during perihelion, charged dust could be directed inward, spiraling along magnetic lines instead of drifting outward. The catch: comets don't usually have magnetic fields strong enough to do that. Then came the stranger interpretations. Some analysts speculated that the jet wasn't a gas plume at all, but an energy emission, a coherent column of charged particles, possibly interacting with the solar plasma. The jet's spectral signature supported this idea. When broken down into wavelength components, it showed an unusual blue ion line, consistent with ionized carbon and oxygen, but missing the thermal continuum expected from heated dust. It wasn't glowing because it was hot. It was glowing because it was energized. The direction of the plume also matched the earlier 1.4 GHz radio anomaly. During the period when the jet was most visible, the rhythmic pulse reappeared. some researchers began to wonder if the two phenomena were linked, if the energy beam and the radio pulse were part of the same process. A natural feedback mechanism could not explain synchronized electromagnetic and kinetic activity. By mid-November, attempts to model the jet's behavior using traditional comet dynamics had failed. When projected forward, the plume's trajectory intersected the solar wind flow in a way that should have dispersed it within hours. Yet the plume persisted for days, stable and focused, almost like a sustained thruster exhaust rather than a diffuse tail. For many astronomers, this was the most disturbing part. Nature produces chaos, diffusion, decay. But what they were seeing from 3i Atlas looked like control. A jet that didn't respond to sunlight but seemed to resist it. A plume that appeared to move not away from the sun but toward a purpose. The dust jet that points the wrong way remains one of the clearest, most visible signs that something about this object defies natural explanation. In that defiance, it mirrors the question running quietly through observatories around the world. If this is not merely venting ice and gas, then what is it doing, and who or what is deciding the direction? When light changes, it tells a story. Every wavelength, every subtle hue carries information about motion, energy, and composition. Astronomers read those colors the way historians read text, line by line, element by element. So when the spectrum of 3i Atlas began to shift toward blue, even by a fraction of a nanometer, it was as if the object had whispered that something fundamental inside it had changed. The earlier spectral readings, taken in late September 2025, showed what everyone expected. A neutral grey-white reflection with faint emission lines for ionized carbon and oxygen. Nothing strange, nothing alien. But after Perihelion, when the object began to accelerate unexpectedly, new data from the European Southern Observatory revealed a subtle but unmistakable drift. A consistent blue shift across the visible and near-infrared bands. A blue shift, in simple terms, means the light is being compressed. When an object moves toward the observer, its wavelengths shorten, nudging colors toward the blue end of the spectrum. The same happens with sound when a siren passes by. The pitch rises as it approaches and drops as it moves away. In cosmic context, the effect is routine. Stars, galaxies, and asteroids all exhibit it depending on their motion. What made this one remarkable was how localized and how variable it was. Instead of a uniform Doppler pattern across all spectral lines, the shift in 3i Atlas appeared only in certain emissions, primarily those linked to ionized carbon monoxide and cyanogen, molecules known to fluoresce under ultraviolet light. The neutral reflection bands, those tracing dust and ice, remained steady. That shouldn't happen. If the entire object were moving toward us faster, all wavelengths would shift together. But they didn't. Only the energetic lines compressed. Something inside 3i Atlas was emitting light that didn't obey the same motion as its outer shell. For days, scientists debated what could cause it. One possibility was jet bias. Light scattering from material streaming sunward could experience a localized Doppler effect, but the directionality didn't fit. The blue shift grew stronger even when the object's relative motion was angled away from Earth. A second theory involved electromagnetic excitation. Perhaps a burst of charged particles from the sun had energized the gas around the nucleus, altering how it emitted light. Yet that too failed to explain the precise periodic nature of the readings. The shift pulsed in intervals of 16 to 17 minutes, the same rhythm as the 1.4 GHz radio pulses detected earlier. That coincidence forced researchers to consider a more complex mechanism. Suppose 3i Atlas isn't simply reflecting sunlight, but modulating it, re-emitting radiation through a layer of ionized material that oscillates in response to internal processes. A plasma sheath like that could alter emission lines selectively, compressing or stretching them depending on charge density and magnetic alignment. In other words, the blue shift might not be a symptom of motion, but of control, an active modulation of light rather than a passive reflection of it. Spectrographs from Mauna Kea and VLT, Perihelion later confirmed a distinct secondary feature, an intermittent polarization swing in the same frequency range. Polarization describes the orientation of light waves, and in comets it usually changes randomly as dust scatters sunlight. Here, the pattern was geometric, alternating between two states like a coded signal. It was faint, subtle, but real, light that seemed to carry rhythm. If the object were natural, The blue shift should have faded as it moved farther from the Sun. Instead, the opposite happened. The spectral compression deepened through November, even as solar intensity fell. The trend reversed only briefly on December 3rd, when the object crossed the Earth-Sun line as if a hidden source of energy had momentarily switched off or reoriented. To some, it looked like a clue, the kind of optical signature that suggests directed energy, possibly a field effect guiding the non-gravitational acceleration already measured. To others, it was merely coincidence amplified by excitement. Either way, the numbers stood firm. 3i Atlas was emitting light at slightly higher energies than before, as if its interior had awakened. The blue shift in its spectrum remains one of the clearest markers of change, not in trajectory, but in identity. Because when light grows bluer, it usually means something is moving closer, and in this case, whether by physics or by intent, 3i Atlas isn't just brightening, it's coming toward us. Orbital windows are quiet intersections, invisible corridors in space where paths almost cross, where velocity, distance, and timing converge with uncanny precision. For Earth, those intersections happen constantly. Every day, the planet moves nearly 3 million kilometers along its orbit around the Sun, creating endless alignments with asteroids, comets, and debris. But not all alignments are equal. Some are mathematical coincidences, and others are opportunities. The upcoming December the 19th, 2025 window with 3i Atlas belongs to the latter category, the moment when our planet and this interstellar visitor come closest in both position and observation potential. The models from NASA's Jet Propulsion Laboratory and the European Space Agency's NEO Coordination Center now predict that, on that date, the Earth will occupy a region of space less than 1.6 astronomical units from 3i Atlas. That distance, roughly 240 million kilometers, may seem enormous, but on the scale of interstellar motion, it's a handshake. More importantly, the object's orbital inclination is almost identical to Earth's, tilted by only about 5 degrees from the ecliptic. This means that for several days around mid-December, both bodies will share nearly the same plane, a flat sheet of geometry stretching around the Sun where their trajectories briefly run parallel. For astronomers, that alignment creates a perfect observational window. From Earth's vantage point, the object won't be hidden behind the Sun, nor drowned in glare, nor lost to the horizon. It will appear in the pre-dawn sky of the northern hemisphere, rising low in Sagittarius, faint but trackable through high-resolution telescopes. The geometry allows uninterrupted observation from multiple continents, with overlapping coverage between Europe, Chile, and Hawaii. For roughly 72 hours, the world's most powerful observatories will all have a clear line of sight to an interstellar object, moving through a corridor of near-Earth space. But this alignment is more than just an opportunity for observation. Dynamically, it also represents a gravitational sensitivity point, a period when small changes in velocity or trajectory could have disproportionate effects on long-term motion. As 3i Atlas passes near Earth's orbital path, even minor perturbations from our planet's gravity could alter its future course. Simulations run by ESA's analysts suggest that, if its velocity vector deviates by even 0.001%, its outgoing trajectory could shift enough to change its escape angle from the solar system by several degrees. That's the difference between a clean departure into deep space and a slow return through the inner solar system decades later. For that reason, the December window has been marked as Priority 1 by every major observatory. The James Webb Space Telescope is expected to dedicate part of its infrared observation schedule to monitor the object's thermal output during those days. The Goldstone Radar Array will attempt a long-range echo scan, while the Allen Telescope Array will continue monitoring the 1.4 GHz signal that first reappeared in November. Even small observatories and amateur astronomers are being invited to contribute optical data, forming the most coordinated global campaign since the detection of Oumuamua in 2017. What's striking about this alignment is how precise it is. Orbital coincidences of this scale, within 1 or 2 degrees of plane and phase, are statistically rare for hyperbolic objects. The probability that 3i Atlas would intersect Earth's orbital corridor within such a narrow margin by chance is less than 1 in 2,000. That number doesn't prove intention, but it does raise the question, how often does random motion produce precision? In quiet terms, scientists are preparing for the possibility that this window may not simply reveal new data. It may test a hypothesis, If the object's acceleration changes as it nears the region of Earth's orbit, it will either confirm or contradict the idea that its motion is reactive, perhaps even responsive to solar or gravitational conditions. Some researchers have gone so far as to describe December 19th as the defining observation point, the night the models will either hold or break. For now, the world waits as the countdown ticks toward that alignment. By mid-December, 3 Atlas will be visible only to instruments, invisible to the naked eye but tracked by hundreds of telescopes at once. And when the clock strikes midnight on December 19th, Earth and the interstellar traveller will occupy the same corridor of space for the briefest moment. 2 bodies passing in silence, bound not by gravity, but by curiosity. In celestial mechanics, probability isn't about luck, it's about geometry. Every orbit, every object, every gravitational influence creates a set of possible futures that can be calculated, plotted, and refined as new data comes in. For 3I Atlas, those probabilities have changed more than once since its discovery. Each new measurement, a brightness variation, a radar echo, a velocity drift, redraws the line that determines where it will go. And in late 2025, that line has begun to curve towards something far rarer than anyone expected, a true orbital intersection with Earth's path. At its simplest, an intersection occurs when 2 orbital planes cross at the same point in space at the same time. The key phrase is at the same time, because space is 3-dimensional, and timing is everything. 1 million comets pass through Earth's orbital distance every decade, but the planet isn't there when they do. The odds of an actual meeting are vanishingly small. For 3I Atlas, the early estimates placed that probability at less than 0.04%, effectively zero. But that was before the non-gravitational acceleration began. When JPL and ESA recalculated the orbital elements after the October course correction, the numbers shifted. The ascending node, the point where the object's trajectory crosses Earth's orbital plane, moved several thousand kilometers inward. The argument of perihelion, which defines how that crossing aligns relative to the Sun, changed by nearly half a degree. Those tiny adjustments tightened the geometry between the 2 paths. As of November's data release, the model predicts that Earth and 3I Atlas will share the same orbital corridor within a window of just 4 days, December 17th through December 21st, 2025. From that alignment, researchers constructed a probability curve, a bell-shaped graph representing the likelihood that the 2 bodies will occupy the same region of space simultaneously. At its centre lies the most probable outcome, a near miss of around 1.4 astronomical units, or roughly 200 million kilometres. But the curve has long, shallow wings, and those wings represent the uncomfortable possibilities. On the outer edge, under low probability but mathematically valid conditions, the miss distance could shrink to under 50 million kilometres, close enough for Earth's gravity to exert a measurable perturbation. The uncertainty stems from 2 main sources: the unresolved acceleration mechanism and the incomplete mass estimate. We don't know how dense the object is, nor whether the acceleration will remain constant. If the thrust persists at its current rate for another 40 days, it could reduce the separation by an additional 10%. If the acceleration vector shifts direction again, as it did in October, the alignment could tighten further. It's a delicate balance between observation and prediction. One new piece of data could collapse the curve into certainty or stretch it back into safety. Statisticians at ESA's Near-Earth Dynamics Office visualize it as a cone, the cone of uncertainty extending outward from the current position of 3I Atlas. At its narrow end, near today's coordinates, the object's location is well defined. Farther out, months into the future, the cone widens, encompassing billions of cubic kilometers of potential space. Within that cone lies a faint thread, the Earth-intersecting trajectory, a corridor so narrow that it's almost invisible yet mathematically possible, and that possibility, even if it's 1 in 1,000, demands attention. Historically, every interstellar object we've detected has followed a clean hyperbolic escape path. None have lingered long enough or crossed close enough to threaten intersection. 3I Atlas is the first to blur that line, an unbound visitor whose trajectory is not just passing through, but adjusting as it goes. That alone alters the curve, because unpredictability in motion multiplies probability in outcome. As December approaches, supercomputers in Pasadena, Darmstadt and Tokyo continue refining the model hour by hour. Each new observation trims the wings of the curve, tightening or relaxing the range. Most likely, 3i Atlas will pass safely through the outer edges of Earth's orbital corridor, unremarkable except for the precision of the alignment. But the phrase, most likely, is doing heavy work. The fact that the probability of intersection isn't zero is what keeps every telescope locked on target. Because in orbital dynamics, certainty is an illusion. Every number, every curve is a measure of what we think the universe will do, until it decides to do something else. And 3i Atlas, for reasons we still don't understand, has been rewriting probability since the day it arrived. In a quiet room inside the European Space Agency's NEO Coordination Centre in Frascati, Italy, a small cluster of high-performance computers has been running the same scenario thousands of times over. Each run begins with a simple instruction: model the trajectory of 3i Atlas from its current position through the end of December 2025. But beyond that line of code lies a universe of uncertainty, forces that shouldn't exist, velocity changes that don't fit equations, and a pattern of motion that seems to rewrite itself every week. The simulations are an attempt to catch up with something that doesn't want to stay predictable. The NEO Coordination Centre, known for tracking asteroids and near-Earth objects, deals in probability, not panic. Its job is to identify potential threats early, calculate impact risks, and provide data to scientists worldwide. Normally, an object's orbit settles into stability after a few updates. By the 10th iteration, the software can predict positions months in advance with confidence down to a few kilometers. But 3i Atlas refused to stabilize. Every new dataset, from JPL, from the Vera Rubin Observatory, from Goldstone, forced the simulations to bend a little further from the previous version. The first wave of simulations in August 2025 portrayed Atlas as a textbook hyperbolic object, its eccentricity measured at 1.18, indicating a clean outbound trajectory. In September, as hints of non-gravitational acceleration appeared, that number rose to 1.24. By late October, after the course correction event, the models were forced to factor in a persistent external thrust. In orbital mechanics terms, that meant adding a variable labelled A1, representing constant acceleration. When the program integrated that variable over time, the results became increasingly strange. Instead of escaping cleanly into interstellar space, some of the simulated trajectories began curving, not inward toward the Sun but sideways, hugging the inner solar system in a long looping path. To test reliability, the analysts ran a Monte Carlo simulation, generating 10,000 potential futures. Each run introduced slight random changes in measured velocity, direction, and solar radiation pressure. In most cases, the object continued outward, brushing the edge of Mars's orbit before fading into darkness. But in 4% of cases, the simulated path intersected Earth's orbital plane within a narrow band of time, December 18th to 21. That fraction was small, but not dismissible. For the NEO Centre, anything above 1% triggers secondary verification. A second set of runs incorporated electrostatic and magnetic interactions, inspired by the unusual spectral and radio data. These weren't standard parameters for comets, but were added to test whether charged plasma around the object could alter its course. The results were inconsistent but intriguing. Electromagnetic drag could account for some of the directional changes, yet it also predicted erratic behavior that has not been observed. The real object was far too stable, its acceleration far too smooth, to be governed purely by chaotic plasma forces. To visualize the results, analysts rendered a 3D probability map, color-coded by confidence level. Most of the plot glowed cool blue, the domain of safe trajectories, but through the center ran a thin yellow filament, representing orbital alignments with Earth. That filament wasn't static, it pulsed slightly, shifting position each time a new observation was added, as though the system itself were alive. Engineers also ran time-dependent density models to estimate potential composition. If the object's mass were lower than assumed, radiation pressure alone could explain some motion. Yet when they lowered the mass below a certain threshold, the model predicted disintegration near perihelion, something that clearly didn't happen. Whatever Atlas is made of, it's stronger and denser than ice, possibly metallic. That density adds another layer of complexity, since heavier bodies are far less affected by non-gravitational forces, and yet Atlas continues to accelerate. The final simulation batch completed on November 30th integrated all available data, radar echoes, optical parallax, and spectral blue shift. The output no longer resembled a simple orbit at all. Instead, the program produced a self-correcting trajectory, one that adjusted incrementally to maintain proximity to the inner solar system before exiting toward the outer planets. No natural object behaves that way. When the analysts plotted the curve, it traced a near-perfect spiral through the ecliptic plane, a path that seemed calculated to intersect observation points: Mars, Venus, Jupiter, and now Earth. Officially, the report concludes with cautious language. Simulations indicate sustained non-gravitational influence consistent with complex internal dynamics. No immediate impact risk has been identified. Unofficially, within those walls, the scientists are beginning to acknowledge what the numbers imply. Every simulation assumes randomness, but 3i Atlas keeps choosing order. Every model predicts escape, but it keeps curving back. And with each new run, the computers return the same quiet verdict: that something out there isn't just moving through our solar system, it's navigating it. For centuries, the mechanics of motion have obeyed a simple truth. To move, something must push against something else. Rockets expel fuel, comets vent vapor. Even photons, the smallest carriers of light, exchange momentum when they strike a surface. In every case, there's an exhaust, a reaction that explains the motion. But 3i Atlas appears to be violating that rule. It's accelerating, steering, and maintaining thrust without shedding any detectable mass. To scientists, that isn't just puzzling, it's revolutionary. When the object first deviated from its projected orbit, the obvious assumption was outgassing. Comets have done it for millennia. Heat from the sun vaporizes ices, creating jets that act as natural thrusters. The effect is small but measurable. However, the infrared and ultraviolet readings from the James Webb Space Telescope showed something strange. No thermal plume, no dust scattering, no sign of volatile gases escaping into space. If Atlas were venting, it should be visible. Instead, the region surrounding it remained clean, almost sterile, as though the laws of momentum were operating in silence. So how does something move without visible exhaust? The first category of explanations remains within physics, just at the edges of it. One theory focuses on photon pressure. Every object absorbs and re-emits sunlight, and that process imparts an almost imperceptible push. It's the principle behind solar sails, which use reflected light for propulsion. But for 3i Atlas, the acceleration is roughly 1,000 times too strong for photon pressure alone. Its albedo, the reflectivity of its surface, simply isn't high enough to generate that much force. A second proposal involves thermal recoil, sometimes called the Yarkovsky effect. If one side of an object radiates heat more efficiently than the other, it can create a continuous push over time. That effect has been observed on small asteroids, altering their orbits subtly over millions of years. Yet the direction of Atlas's acceleration doesn't align with its thermal emissions. Its spectrum shows no consistent hotspot or rotation-induced heating pattern. Whatever is driving it seems to operate independently of temperature. Then there's electromagnetic propulsion, a far more speculative avenue. If the object carries a strong magnetic field or interacts dynamically with the solar wind, it might be converting charged particle energy directly into motion. Some researchers at ESA modelled it as a plasma sail, a theoretical device that uses magnetic fields to deflect solar wind protons, creating thrust without ejecting mass. But such a mechanism would require continuous field adjustments and immense energy stability. It would in essence function as an engineered system, not a comet. The absence of exhaust isn't just a visual oddity, it has thermodynamic implications. If energy is being produced or converted, where does it go? The radiative signature of 3i Atlas hasn't changed in proportion to its acceleration. There's no infrared spike, no heat plume, no excess radiation in ultraviolet or microwave frequencies. It's as if the energy powering its motion is contained perfectly, an efficiency no known natural process can achieve. This brings scientists to the edge of a troubling thought. If 3i Atlas is not producing detectable exhaust, it might not be producing motion in the conventional sense at all. Perhaps the object is manipulating spacetime directly, exploiting curvature rather than force, adjusting its local frame of reference instead of pushing through it. The idea sounds extreme, yet it neatly explains the data. smooth acceleration without heat, thrust without reaction, and trajectory control without chaos. At JPL, researchers refer to this paradox as the quiet drive. It's shorthand for any phenomenon that generates acceleration without releasing momentum carriers. So far, it exists only as a placeholder in equations, a variable to keep the math balanced while the physics remains unsolved. If 3I Atlas is truly using energy without exhaust, it's not merely an anomaly, it's a demonstration. It suggests that propulsion, as we understand it, might not be the only way to move. Whether that mechanism is natural, electromagnetic, or something more advanced, one fact has become inescapable. 3I Atlas is not coasting through space, it's operating in it. And in that quiet operation, motion without friction, energy without flame, lies the most profound question yet. Is this object obeying the universe, or teaching it a new rule? Every object that enters the inner solar system carries a chemical fingerprint, a pattern of elements and compounds that tells the story of where it was formed and how it has changed. For comets, those fingerprints almost always include water vapor, carbon dioxide, and dust. But when the James Webb Space Telescope turned its infrared spectrometer toward 3I Atlas in late October 2025, the results didn't fit any known pattern. Instead of water dominating the spectrum, one line rose above all the rest, a sharp, narrow band at 4.7 micrometers, corresponding to carbon monoxide. The first detection came quietly. Webb's NIR spec instrument recorded an unusually strong CO emission line, 8 times more intense than the nearby water line. At first, researchers thought it was a calibration glitch, perhaps a reflection artifact from the telescope's mirror. But when the infrared telescope facility in Hawaii confirmed the same feature days later, doubts vanished. The signal was real. 3I Atlas was outgassing carbon monoxide in concentrations never before observed in a comet or interstellar object. That ratio, 8 parts CO to 1 part H2O, immediately attracted attention because it's backwards compared to what the sun's heat should produce. Near perihelion, water ice sublimates easily, while carbon monoxide requires colder conditions to remain trapped. Once a body moves close to the sun, CO usually burns off first, leaving water as the dominant volatile. Atlas was doing the opposite, losing almost no water but releasing a continuous, stable stream of carbon monoxide. The chemical logic had flipped. Understanding why required looking deeper into physics. Carbon monoxide isn't just a gas, it's an energy carrier. It forms in oxygen-poor environments under extreme cold and can survive intact for billions of years in interstellar space. When it finally warms and reacts with other compounds, it releases energy, not as heat, but as infrared radiation. If 3I Atlas were rich in CO, that radiation could, in theory, power a self-regulating reaction cycle, generating controlled internal heat without visible exhaust. Some analysts quietly began calling it the cold engine hypothesis, the idea that the object wasn't simply venting gas but using it. There's precedent for small bodies rich in carbon monoxide. The comet C2016 R2 Pan-STARRS, for example, showed high CO levels in 2018. But even that case peaked at a ratio of about 2.1, nowhere near the dominance seen in 3I Atlas. Moreover, R2's emission was chaotic, with fluctuating brightness and visible jets. Atlas's signature, by contrast, is steady and coherent, its CO line barely changing in intensity over several weeks. The pattern looks less like random sublimation and more like regulation, as though the gas release were being moderated from within. The spatial distribution of the emission adds another layer of intrigue. High-resolution spectroscopy from the VLT in Paranal found that the CO wasn't diffused evenly around the nucleus. Instead, it appeared concentrated in a narrow equatorial band only a few kilometers wide. The gas exited at nearly constant velocity, creating what the data describe as a linear vent, a feature rarely, if ever, seen in natural comets. That geometry coincides with the direction of the object's observed acceleration vector. In other words, the carbon monoxide isn't just leaving the surface, it's leaving along the same line that's propelling the object forward. If this were random, the distribution would be chaotic, venting from fractures all over the surface. But 3I Atlas's output behaves more like a controlled nozzle than a collection of vents. The spectral purity of the CO also stands out. Almost no carbon dioxide contamination, no sulfur traces, no mixed hydrocarbons. Such chemical cleanliness is virtually impossible in a natural body formed from random accretion. It suggests refining, separation, or at least selective release. Officially, the European Space Agency classifies the anomaly as dominant CO emission, likely resulting from deep-core volatile reservoirs. Unofficially, several researchers have proposed that this may be more than mere chemistry. It could represent an energy system, perhaps converting CO oxidation into heat or electrical charge. If true, that would explain the sustained acceleration without visible exhaust and the constant internal temperature despite changing solar flux. For now, the carbon monoxide signature remains one of the most puzzling clues in the entire 3I Atlas story. It's chemistry that behaves like engineering, fuel that doesn't burn, gas that doesn't scatter, an emission that aligns perfectly with motion. Whatever is happening inside that object, it's organized. And in the language of science, organized is another word for designed. Between Mars and Earth lies a narrow gravitational highway, a corridor of low-energy orbits that space agencies have used for decades to move spacecraft efficiently between the two planets. In celestial mechanics, it's known as a Hohmann transfer window, a path that allows an object to shift from one orbit to another using minimal propulsion. For most missions, this window opens roughly every 26 months. For 3I Atlas, it opened by coincidence, or design, in late 2025, precisely as the object crossed the inner solar system. What startled mission planners and orbital analysts alike was that Atlas's trajectory wasn't just passing through this corridor, it was aligned with it. The Mars-Earth transfer corridor is a kind of invisible lane carved by the physics of gravity. When a spacecraft leaves Mars, it must accelerate enough to raise its orbit outward until it intersects Earth's path. The process takes energy, and most importantly, timing. The corridor only exists when both planets are in the correct positions, Mars trailing Earth by a specific angular separation of about 44 degrees. In October and November of 2025, that separation was exact. In that same period, 3I Atlas happened to move from 1.5 astronomical units near Mars's orbit toward 1.0, the region Earth occupies. On paper, that could be coincidence. But when analysts at ESA's NEO Coordination Center compared Atlas's flight path with known optimal transfer trajectories used by Mars probes, the match was nearly perfect. The object's heliocentric velocity vector, its direction of motion relative to the Sun, was offset by less than 3 degrees from the mean trajectory used for spacecraft departing Mars toward Earth. In simpler terms, if Atlas were a human-made probe, it would be flying the exact path engineers would choose for a Mars-to-Earth mission. That realization sent researchers back to older data. The object had passed within Northern-Light astronomical units of Mars in early October, close enough for its path to be influenced slightly by the planet's gravity. That encounter was unremarkable in energy terms but significant in geometry. The gravitational slingshot effect, tiny but measurable, altered Atlas's inclination just enough to bring it into the transfer plane between Mars and Earth. The timing was exquisite. The course adjustment happened days before the observed October course correction, and the resulting vector pointed straight along the interplanetary corridor. For a natural comet, that sequence would require extraordinary luck. Orbital simulations run by both NASA's JPL and ESA show that the probability of an unbound interstellar body randomly aligning with an interplanetary transfer orbit between two habitable worlds is less than 0.03%. Yet that's exactly what happened. The alignment isn't rough or approximate, it's refined, guided, as if something, or someone, had been calculating the same equations used in mission planning centers on Earth. What's more intriguing is the velocity profile. The average speed of 3I Atlas during this transition phase is about 58 kilometers per second, slightly higher than the optimal 52 kilometers typically required for a Mars-Earth Hohmann transfer. That excess energy places it in what engineers call a fast transfer trajectory, a path that shortens travel time at the expense of precision, useful if the goal is reconnaissance rather than arrival. It's a corridor that a probe might use to observe without lingering. Astronomers began to notice subtle synchronizations. The window of closest approach to Earth, December 19, 2025, aligns almost exactly with the point of intersection predicted by this fast transfer curve. That means the trajectory isn't only similar in shape to a Mars-Earth corridor, it's synchronized in timing. Every model tracing, Backward through Mars's sphere of influence shows that if Atlas's acceleration had started just 12 days earlier or later, it would have missed this perfect alignment altogether. To some scientists, this is simply celestial coincidence magnified by human pattern recognition. Space is vast and random alignments happen, but others are less certain. The corridor between Mars and Earth isn't just any route. It's a bridge between two worlds capable of supporting life. The last time an object passed near Mars, it moved on toward Venus and Jupiter. This time, its trajectory has curved inward, toward us. Whether it's natural or not, 3i Atlas has entered the same gravitational lane we designed for ourselves, the route that connects the red planet and the blue one. And as it glides silently along that invisible road, its presence forces us to ask an unsettling question. Is this object merely following gravity, or is it following us? Every planet carries an invisible shield, a magnetic cocoon that protects it from the charged particles streaming outward from the Sun. For Earth, that shield is the magnetosphere, a vast bubble that stretches more than 60,000 kilometers toward the Sun and trails 1,000,000 kilometers behind the planet like a comet's tail. Whenever a foreign object crosses near this region, even at great distances, electromagnetic interactions become possible. And as 3i Atlas drifts steadily toward the ecliptic plane, astronomers are beginning to prepare for just such an encounter. Predictions released jointly by the European Space Agency and NASA's Heliophysics Division suggest that, around December 17th of 2025, the interstellar object's trajectory will place it within range of Earth's outer magnetic influence. Not within the magnetosphere itself, that's still hundreds of thousands of kilometers away, but close enough for field coupling to occur. When the magnetic field of an external body interacts with the solar wind in the vicinity of another planet, complex electrical structures can form, shock fronts, current sheets, and oscillations in plasma density. These are the same phenomena that make Earth's auroras shimmer and flicker. To predict how 3i Atlas might behave in such an environment, scientists began by estimating whether the object could generate its own magnetosphere, even a weak one. The theory isn't far-fetched. Many comets develop induced magnetic fields when the solar wind collides with their ionized gas clouds. The result is a temporary miniature magnetosphere that deflects charged particles. Normally this effect is faint, microtesla's at most, and localized. But Atlas has already shown itself to be unlike any natural comet. Its ion emissions are unusually stable, and its orientation relative to the solar wind remains constant, suggesting internal regulation rather than random venting. If that's true, the object might possess a persistent magnetic envelope, either generated by plasma flow or intrinsic magnetization. In that case, when it approaches Earth's field boundary, the bow-shock region where the solar wind slows and diverts, the two magnetic systems could interact directly. Simulations run on ESA's Helios supercluster modeled this possibility, using data from the solar wind magnetohydrodynamic archive. The results were startling. The model predicted a series of synchronized wavefronts rippling along the magnetopores, each spaced roughly 16 minutes apart. The same periodic interval as the 1.4 GHz radio pulse associated with the object. That pattern implies coupling. In simpler terms, if the object's magnetic field oscillates in time with its radio emission, those oscillations could imprint themselves on the solar wind, creating measurable fluctuations detectable from Earth. The Cluster 2 and Themis satellites have been programmed to monitor for precisely such disturbances. Should they appear, the data could confirm that 3i Atlas is generating structured electromagnetic activity rather than passive reflection. Even more provocative is the possibility of energy transfer. When two magnetospheres interact, they can exchange plasma and electrical potential, effectively charging each other. If Atlas carries a conductive or metallic surface, it could experience Lorentz forces, small but measurable accelerations caused by its movement through Earth's magnetic field lines. That could alter its velocity or orientation without any chemical propulsion at all, giving the appearance of active maneuvering. The theoretical consequences don't stop there. Some plasma physicists have speculated that if Atlas's field is resonant, tuned to certain frequencies of the solar wind, it might amplify those currents, producing detectable radio bursts. Instruments like LOFAR in the Netherlands and Parker Solar Probe's FIELDS instrument will be listening for sudden spikes in low-frequency electromagnetic noise during the December window. What makes this scenario so unusual is the precision of timing. The projected intersection between Atlas's solar wind wake and Earth's magnetotail occurs just as the planet passes behind the Sun relative to the object. In other words, Earth's shadowed side, the night side magnetotail, will be aligned with Atlas's inbound path, creating an environment of low solar interference and maximum sensitivity for detection. If anything unusual happens, we'll see it in our instruments first, not our skies. No one expects a direct physical encounter, but if the simulations are right, Earth's magnetic envelope will feel the whisper of 3i Atlas as it passes, a ripple in the field, a pulse of current, perhaps even a faint radio hum. It will be the first time in history that our planet's magnetosphere interacts with an object born between the stars, and whether that encounter ends quietly or with measurable resonance, it will confirm one thing. Beyond doubt, 3i Atlas isn't just drifting through space. It's leaving electromagnetic fingerprints wherever it goes. Orbiting Earth is a fragile halo of dust, fragments, and remnants of human ambition. Every satellite launch, every booster stage, every collision leaves behind microscopic particles of aluminum, ceramic, and steel. Together, they form what scientists call the orbital debris cloud, a swarm of material encircling the planet from about 160 kilometers above the surface to beyond 36,000 kilometers, where geostationary satellites drift in near-permanent equilibrium. It is humanity's artificial ring, invisible to the naked eye yet constantly monitored. When analysts at the European Space Operations Centre realised that 3i Atlas might align with Earth's orbital plane, in December 2025, one question arose immediately. What happens if it passes through that cloud? The object will not approach close enough to collide with Earth, but depending on its trajectory angle, it could intersect the outer layers of our orbital debris field, a region populated by both defunct satellites and high-velocity particles the size of sand grains. That possibility has triggered a new wave of simulation and concern. At its current velocity, roughly 58 kilometers per second relative to the Sun, Atlas is moving nearly 50 times faster than the average piece of Earth's space junk. Even a glancing interaction with debris would create an extraordinary burst of energy. A particle smaller than a marble hitting at that speed would release more kinetic energy than a hand grenade. On a macroscopic scale, the object would be unaffected, but the consequences for observation could be dramatic. The collision could generate microplasma flashes, electromagnetic noise, and even visible streaks of light detectable from orbit. ESA's Space Debris Office in Darmstadt has been running high-resolution impact simulations since early November. Using trajectory data from the Joint Space Operations Centre, the team mapped where Earth's artificial debris belts intersect the projected path of 3i Atlas. The results show that if the object's acceleration continues along its current vector, it could graze the translunar debris region, an area roughly 60,000 to 80,000 kilometers from Earth, populated by spent rocket stages, defunct satellites, and small fragments from decades of spaceflight. It's a sparse environment, but even one impact at interstellar velocity would produce detectable phenomena. The risk isn't collision in the catastrophic sense. The object is too massive, its course too shallow. The real concern lies in the potential data contamination such an encounter could cause. Any plasma burst or reflective plume generated by impact could distort radio observations and radar readings, producing misleading signatures that mimic artificial activity. Ironically, an entirely natural debris collision could make Atlas look more engineered than ever, briefly lighting it up, perhaps even creating the illusion of a controlled maneuver. But there's another deeper question, one that goes beyond mechanics. Humanity's debris cloud is a record of our technological presence, a kind of electromagnetic calling card encircling our planet. If Atlas truly is more than a natural comet, if it possesses any capacity to sense or analyze its surroundings, then passing through this ring of wreckage might serve as an introduction. Our discarded fragments, solar panels, bolts, metallic shards, could become the first man-made materials an interstellar object ever encounters. Some researchers at NASA's Orbital Debris Program Office have speculated about potential electromagnetic feedback effects. Many of those fragments carry residual charge from constant exposure to solar wind. A high-speed body like Atlas passing nearby could induce brief discharges, electrostatic arcs, visible as radio noise or momentary light bursts. Instruments like the DSN's Canberra station and LOFAR are being calibrated to watch for these anomalies during the December window. If any interaction occurs, it will be fleeting, perhaps a few seconds of plasma turbulence and radio static, but scientifically priceless. Measuring such an event could reveal properties of the object's composition, conductivity, magnetization, and even surface texture. In other words, Earth's own debris cloud might unintentionally probe the interstellar traveller for us. Whether Atlas sails through untouched or leaves a trail of electromagnetic echoes, one fact remains sobering. Humanity has surrounded its world with a thin fog of machinery and metal, and now, for the first time, something not of this world may pass through it. It will be a silent collision of civilizations, one born of industry, the other of the stars, meeting briefly in the space between orbits, before each continues on its way. When the first faint pulse at 1.4 GHz was detected near 3I Atlas, most scientists dismissed it as coincidence. The hydrogen line, after all, is a common cosmic frequency. But as weeks passed and the signal returned again and again, stable, rhythmic, and synchronized with the object's rotational window, the conversation inside observatories began to change. It wasn't proof of communication, but it was structured. Now, with the object nearing Earth's orbital plane, and its electromagnetic activity growing stronger, the idea once whispered at conferences is being spoken aloud again. What if 3I Atlas isn't just an object to observe, but one that transmits? The so-called communication theory first appeared informally in internal memos at the SETI Institute and ESA's Deep Space Science Division after the initial detection in October. The hypothesis was simple yet bold, that the periodic 1.4 GHz pulses and the corresponding blue shift variations in the optical spectrum represented intentional modulation, not a natural resonance, but a form of structured data transmission. According to the theory, the object's periodicity, precisely 16 minutes and 42 seconds, could serve as a timing marker, similar to how early human radio transmissions used carrier waves before embedding information in them. The theory gained traction after the Allen Telescope Array identified a secondary modulation pattern hidden within the main pulse envelope, a subtle amplitude variation repeating every 4 cycles. When Fourier transformed, the pattern resolved into harmonic intervals that matched the frequency spacing of atomic hydrogen's hyperfine transition. That's a kind of mathematical handshake, a way to say, I understand physics without using language. No random plasma burst or magnetic oscillation has ever produced such clean harmonic spacing. Still, scientists hesitate. The skepticism is not because the data are weak. They're consistent across multiple instruments, but because the implications are immense. Natural explanations are always preferred until exhausted. Some argue that 3I Atlas might be behaving like a natural maser, amplifying radio waves through stimulated emission in its carbon monoxide-rich coma. Others propose resonant magnetohydrodynamic waves within its plasma sheath, driven by the solar wind. Both models can mimic periodic radio signals, but neither can maintain stability for weeks at a time. What reignited the theory in late November were the synchronization events, instances where the object's radio pulses appeared to slightly adjust their frequency drift to match the Doppler shift of Earth's motion. In other words, the signal compensated for our planet's orbit, as if aware of the changing geometry. Statistically, it could be coincidence, or it could be awareness of alignment. The coincidence occurred twice, each within hours of ground-based transmissions directed at the object for radar ranging tests. That timing is what forced scientists to reconsider the possibility of interaction. The communication theory doesn't claim intent in the human sense. It suggests that 3I Atlas may operate as a beacon, an autonomous transmitter, embedded in a moving structure, programmed to activate when conditions align. Under this model, the object isn't signaling Earth specifically, but broadcasting diagnostic or survey data as it traverses solar systems, much like a probe sending telemetry back to a parent source. The key feature supporting this view is energy discipline. The pulses are narrowband, consistent, and remarkably energy efficient. If one intended to communicate across interstellar distances, this is precisely how one would design the system. SETI's signal analysis team has now begun encoding the incoming data as binary series to check for non-random sequences, prime numbers, Fibonacci intervals, or repeated phase inversions. So far, nothing overtly artificial has been confirmed, but the work, continues under quiet confidentiality. Officially, agencies refer to it as an electromagnetic behaviour study. Unofficially, the conversation has moved to what a response would mean, or whether sending one would even be wise. The older skeptics remind everyone that extraordinary claims require extraordinary evidence. Yet the younger analysts, those who grew up watching humanity's own probes, leave the solar system, look at 3i Atlas, and see something hauntingly familiar. Its timing, its precision, its silence between bursts, all mirror how our own spacecraft speak when they are far from home. No one dares call it a message. But as the object nears the intersection of its path and ours, every dish on Earth will be listening. Because whether it's noise, physics, or something with purpose, the one truth shared by everyone studying it is this: communication doesn't begin with understanding, it begins with recognition. And 3i Atlas, for the first time, is beginning to look like it recognizes we're here. For all the data collected, the radar echoes, the photometric curves, the magnetic readings, and the repeating radio pulses, there remains a quiet unease in the scientific community. Every number fits within its own narrow frame of logic, but when those frames are assembled together, they don't form a picture that makes sense. The more precisely we measure 3i Atlas, the less natural it appears. What's emerging is not a lack of data, but a lack of coherence. The numbers tell us what is happening, but not why. Mathematically, the object's trajectory is understood down to a few hundred kilometers. Its velocity, currently just over 58 kilometers per second, has been confirmed by independent observatories across 3 continents. Its light curve shows no chaotic spin, no tumbling that would cause erratic acceleration. Its spectral lines reveal an abundance of carbon monoxide, almost no water, and a faint but persistent blue shift that refuses to fade. Those are facts, hard, measurable and replicable. But the problem is that these facts shouldn't coexist. Take the acceleration. Every model based on solar radiation outgassing or thermal lag fails to reproduce the observed thrust. To sustain that motion, Atlas would need to emit material at a rate high enough to be visible from Earth, yet it remains visually pristine. The spectral data show no dust plume, no coma expansion, no fluctuating brightness. It's as if the object is being pushed by a hand we cannot see. And if it's not expelling mass, then the principle of conservation of momentum, one of the pillars of physics, is being bent. Then there's the spectral paradox. The carbon monoxide signature is clear, yet the ratio between ionized and neutral carbon is inverted. Normally, sunlight strips electrons from those molecules as they escape into space, producing a predictable distribution. In Atlas, the ionization level fluctuates in sync with its periodic 1.4 GHz radio pulse. That correlation has no precedent in natural objects. It suggests that whatever is emitting those radio waves might also be controlling the ionization process, as if chemistry, magnetism, and signal transmission are all parts of one system. The magnetospheric data deepen the confusion. ESA's simulations predict that Atlas should have developed a diffuse, irregular plasma sheath as it travelled through the solar wind. Instead, measurements of its reflected polarization indicate an extraordinarily stable electromagnetic field geometry, not chaotic like a comet, but symmetrical, self-correcting. This level of consistency implies feedback, the kind of fine-tuning seen only in engineered systems or self-regulating plasmas. Even its brightness variations defy randomness. The light curve oscillates with a smooth, sinusoidal rhythm every 9 hours and 12 minutes, matching the object's suspected rotational period. But superimposed on that pattern is a faint modulation, a subtle heartbeat, every 16 minutes, echoing the radio signal interval. If it's coincidence, it's one that nature rarely repeats. So the question becomes, are we misinterpreting the data or witnessing a process we don't yet understand? The conservative answer is that our models are incomplete. Perhaps there are undiscovered forms of cryovolcanism or magnetic propulsion that can mimic control. Perhaps the carbon monoxide reservoir lies deep below a metallic crust, releasing gas through unseen vents. Perhaps the radio pulse is a natural resonance within an ionized plasma cavity. Each of those explanations could solve one piece of the puzzle, but never all of them at once. When scientists gathered for the International Astronomical Union's emergency session in Geneva, the tone was cautious but unified. The consensus wasn't that Atlas was artificial. It was that the data no longer obeyed any single natural framework. As one researcher phrased it, every measurement answers one question and creates two new ones. In the end, what the numbers don't yet explain is the coherence itself. Why does every anomaly, magnetic, spectral, kinetic, align in time as if orchestrated? Why does each data point fit into a rhythm rather than chaos? Nature is complex but rarely this consistent. For now, the equations hold the evidence but not the meaning. And in that silence between what we can measure and what we can explain lies the heart of the mystery. Atlas isn't defying science, it's demanding that we expand it. By early December 2025, a quiet sense of urgency had spread across the world's observatories. The calculations were converging. 3i Atlas would cross Earth's orbital plane between December 17th and December 21st. It wouldn't collide, but it would pass close enough, both geometrically and magnetically, to offer a once-in-history opportunity. Within days, agencies that had never collaborated on an interstellar object before were coordinating a synchronized global campaign. The goal was simple in writing, but nearly impossible in practice. Capture every possible form of data from every spectrum at the same time. The plan began at ESA's Operations Center in Darmstadt, where representatives from NASA, JAXA and private observatories joined through a secure interagency link. The mission architecture resembled a planetary defense drill, but this time the target wasn't a threat, it was a question. The schedule was divided into 3 observation phases: approach, crossing and outflow. Each phase required its own set of instruments and timing. During the approach phase, December 10-16, optical telescopes would lock onto the object to refine trajectory data. The Vera C. Rubin Observatory in Chile would take continuous wide-field images every 90 seconds, providing parallax data for precise positional tracking. In parallel, the James Webb Space Telescope would use its NR-spec instrument to monitor thermal emissions and chemical spectra, especially the volatile carbon monoxide line that had puzzled scientists for months. The intent was to detect any pre-encounter variability, hints that 3i Atlas was adjusting course again, or shedding material before entering the magnetically active region around Earth. The crossing phase, December 17-21, would be the heart of the campaign. Radar arrays, Goldstone in California, the Greenbank Telescope in West Virginia, and the ISCAT system in northern Scandinavia would transmit synchronized pings toward the object, measuring its distance, shape, and potential spin. The Very Large Array and LOFAR in the Netherlands would handle radio monitoring, tuned specifically to the 1.4 GHz band that had exhibited periodic pulses. If those pulses changed, in strength, modulation, or frequency drift, it would be the clearest sign yet that the object was responding to its new environment. Meanwhile, orbiting satellites would watch from above the atmosphere. The Parker Solar Probe, though far from Earth, would measure changes in solar wind density and magnetic alignment. The Themis constellation in Earth's magnetotail would record any fluctuations in plasma currents, particularly the kind of ripples ESA's simulations had predicted. Even the International Space Station's external sensors would be used to detect possible particle flux changes as Earth's magnetosphere flexed. For the outflow phase, December 20th-26, attention would shift to follow-up spectroscopy and data correlation. The Hubble Space Telescope would observe the faint trail left behind, if any, to determine whether the object had lost mass or interacted with solar particles during the encounter. Meanwhile, data centers in Pasadena, Geneva, and Tokyo would synchronize petabytes of incoming data, using real-time telemetry pipelines designed for planetary defense. In total, more than 50 observatories and 10 orbital platforms would contribute. One of the most debated elements of the campaign was whether to attempt active communication, to transmit a controlled signal toward the object during the crossing window. NASA's Jet Propulsion Laboratory proposed a short radar-encoded pulse, not as a greeting, but as a calibration test. The frequency would match the hydrogen line, modulated by a binary prime number sequence. Officially, it was a test of radar reflection delay. Unofficially, it was a whisper into the dark, to see if anything whispered back. Across the scientific world, the tone was a mixture of excitement and restraint. For most, this was a once-in-a-lifetime experiment, the first interstellar object studied in coordinated real time from Earth's surface to the edge of the magnetosphere. For others, it was a test of humility, an encounter with something that kept defying explanation, even as the best instruments humanity had ever built turned toward it. By December 15th, as the last calibration signals were sent, a single line circulated through internal ESA channels, half mission directive, half philosophy: record everything, assume nothing, because whatever happens next, the universe will not repeat it. For decades, the question of contact preparedness, how humanity should react to the detection of an extraterrestrial signal or artifact, belonged to philosophers, not physicists. It was the realm of speculation, panel discussions, and science fiction. But as 3i Atlas continues to behave in ways that strain the limits of natural explanation, that once hypothetical conversation is starting to move from symposiums to mission control rooms. The ethical question is no longer if we should prepare for contact, but how we should prepare, and who, if anyone, has the authority to decide what happens next. At the core of this dilemma lies a paradox. Science demands neutrality, gather data, test hypotheses, avoid assumption. Yet neutrality becomes fragile when the evidence itself suggests intentionality. If the 1.4 GHz pulses, the non-gravitational acceleration, and the spectral coherence of 3i Atlas are more than random, then the object might not merely be a discovery. It could be an encounter. And encounters demand decisions. Do we respond? Do we wait? Do we even announce what we've found before we understand it? Inside ESA's Near-Earth Object Coordination Center, quiet protocols have already been discussed. In a locked meeting room, a small interdisciplinary panel, astronomers, ethicists, linguists, and representatives from the United Nations Office for Outer Space Affairs have been drafting what they call the Interstellar Contact Framework. The document isn't public, but its existence acknowledges a reality that few agencies want to admit. Contact preparedness cannot begin after contact occurs. It must begin now, while uncertainty still allows calm. The framework addresses 3 tiers of action. Observation, the first, covers how to confirm authenticity and maintain scientific transparency without triggering panic. It dictates that no signal or object should be labelled intelligent, until independently verified by at least 3 institutions using separate instruments. Interpretation, the second, deals with decoding, the analysis of patterns, possible intent, and potential communication protocols. The final tier, engagement, is the most controversial. If a response seems warranted, who speaks for Earth? History offers little guidance. In 1977, the WOW signal sparked momentary fascination but no coordinated response. In 2017, Oumuamua challenged models but not politics. 3i Atlas, however, occupies an entirely different category. It is not only visible and measurable, it's behaving in a way that seems to acknowledge our observation. If it reacts to signals sent from Earth, even passively, the debate about whether to communicate becomes an ethical imperative. Silence, too, is a form of communication. Ethicists argue that any premature transmission could have profound consequences. A poorly structured signal might reveal too much about our technology or environment. It could even be misinterpreted as hostility. The SETI post-detection protocols, written in the 1980s, recommend global consultation before any outbound transmission. But those guidelines were written in an era when contact felt hypothetical. In practice, real-time communication decisions might unfold too quickly for bureaucracy to catch up. Philosophers frame the issue in simpler terms. What does responsibility mean when facing something we might not understand? If 3i Atlas is transmitting purposefully, its behavior may be entirely benign, perhaps exploratory, perhaps observational. But if it is a probe, a sentinel, or a relic of something greater, then the ethics of interaction shift from curiosity to caution. Some argue that engaging it could risk interference with an autonomous system of unknown origin. Others insist that avoiding contact would waste the most significant opportunity in human history. Governments are watching quietly. Publicly, they defer to science. Privately, defense agencies are running scenario analyses, not because they expect hostility, but because any object capable of maneuvering between planets without propulsion raises geopolitical questions about power and control. In that tension between wonder and fear lies the true ethical weight of the moment. As December approaches, and humanity's instruments prepare for their closest look yet at 3i Atlas, the silence around official communication policy is telling. For the first time, we're no longer alone in the equation of discovery. We are participants within it, And whether the object is a messenger, a machine, or merely a mirror reflecting our curiosity back at us, the ethical challenge remains the same. How do you speak responsibly to something that might already be listening?